Chapter 10.7 deals with exponential growth and exponential decay. And basically what we're doing is we're taking all of our logarithms and our exponents and we're just doing a bunch of applied word problems to them. And so the only thing you guys really need to remember is this formula here. Sometimes you'll hear other people call it as PERT formula. That's what I tend to refer to it as. And it's basically A equals PE to the RT. And so what you got to do is you have to memorize this formula. And in a later video, I'll go and derive this for you guys. That way you guys know where it comes from. It didn't just suddenly randomly appear out of nowhere. This formula actually does appear. E does play an integral role in it, but we'll figure all that out later on. And you guys got to kind of memorize these rules here, that A is equal to the resulting amount of stuff, whatever it is, whether you're learning about, the population of bunnies or bacteria or the half-life of whatever. P is the principal or the initial amount of stuff, whatever it is you're dealing with. Again, bunnies, bacteria, whatever. E is equal to E, which is Euler's number, that magical 2.71-ish type number. R is the rate of growth or decay, and T is the time. The hardest thing about these problems is reading them and understanding what it is you're actually looking for. So your assignment is the worksheet, and go ahead and download it through Learning Point, and we'll just go ahead and do a bunch of the problems on there so that you guys can kind of get a feel for what we're looking for here. So the first problem here is number 1, and it says here a strain of bacteria can grow from 30 to 195 organisms in 5 hours. Find the growth constant. Okay, so let's break this problem down a little bit. It says that the strain of bacteria, I'm going to go ahead and underline this and catch up here. A strain of bacteria can grow from 30 to 195 organisms in 5 hours. So the first sentence is down. What we need to do is we need to extrapolate what information we can gather from this. Well, 5 hours, that's got to be time. There's no other way. There's no other thing that can be. So that should be T. 30 to 195, well, unless the bacteria is dying, then we can assume that 30 is the initial amount, which is the principal amount, which is P. Now, I can assume that because it says the bacteria will grow, which means that the rate of change is going upwards. If it says that it will die from 195, then 195 would have been my initial. But because it's growing, 30 is the initial. Obviously, 195 is going to be the final amount, or the resulting amount. And now we're trying to find the growth constant. Well, find the growth constant, that sounds to me like rate of growth. So let's go ahead and plug all this stuff in. It's 195. It's going to equal 30 times E. Well, E is E to the R. Well, R is 5, and then T. Okay, so let's go ahead and do some calculator work here. I'm going to go ahead and divide everything by 30. So I have 195 divided by 30. That is 6.5 equals E to the 5t. Now here's where things are going to get a little funny. What I'm going to do is, just like in the last section, I'm going to take the natural log of both sides. And what I have is the natural log of 6.5 is equal to the natural log of E to the 5t. Now I'm going to go ahead and use my properties of logarithms to back the 5t down, and I have natural log of E equals the natural log of 6.5. Now, this natural log of E, if you guys remember from a previous video, well, natural log's base is E. So what I'm really doing is I'm taking the log base E of E, and we know that when we have logarithms that have the same base and answer, they equal 1. So that's really 5t times 1, or I can get rid of the natural log of E. So what I really have is 5t is equal to the natural log of 6.5. I'm going to go ahead and divide by 5 on both sides. So I have t is equal to some number, and that's going to be the natural log of 6.5 divided by 5, and that's going to be 0.374 about. With these problems, there's something that could occur that's called rounding error, and that could throw you off by a little bit. So just make sure you guys are rounding to the nearest 3 decimals. Try not to round anything halfway through the problem, because that could really throw your problem for a bit of a loop, and then you're kind of in trouble. All right, so I'm going to go and pause and upload the next problem. Hold on. Problem 2 says a substance decays or decomposes radioactively. Its half-life is 32 years. Find the decay constant. Okay, we are trying to find the decay constant this time. Well, if you remember from the last problem, the growth constant was r. In this case, the decay constant is also going to be r. All right, so why don't we say r equals, well, that's what we're trying to find out. E is going to equal E, P is going to equal something, and A is going to equal something. And T is going to equal, well, it looks like 32 years, right? Okay, here's the thing with a half-life problem, is that the initial amount is always going to be double the resulting amount because we're dealing in half-life, right? We're trying to figure out how long it takes for a substance to turn into half of itself. So if the initial amount of radioactive material was, say, 2, then what that means is that the resulting amount is going to be 1, right? Because 1 is half of 2. I can choose any combination of numbers I want. If I chose the initial amount being 30, that means that the resulting amount needs to be 15. I think you're getting the idea here. If I chose, say, let's say I chose 32, then it would be 16. If I chose 128, it would be 64, blah, blah, blah. I think you guys kind of get the idea by now. So I'm going to, for simplicity's sake, I'm going to choose 2 and 1 as my P and as my A, which means that A equals PE to the RT. So A is 1, and that's going to equal 2E to the R. Well, in this case, R is what I'm trying to find, and then T is going to be 32. Now we're back to kind of where we started. I'm going to divide both sides by 2, so I have 1/2 equals E to the 32R. I'm going to take the natural log of both sides, so I have the natural log of, I'm going to go ahead and just change this to a decimal, of 0.5 equals, I'm going to go ahead and set my, I'm going to go ahead and set the equation up first, so 32R times natural log of E, and the natural log of E is going to go away as we saw in the last problem. So I'm going to go ahead and divide both sides by 32. So I'm going to take the natural log of 0.5, and I'm going to divide that by 32. So R is approximately equal to negative 0.0217. All right, and we should have expected a negative rate because the decay constant, where if something's decaying, that means it's decreasing in size. All right, let me go ahead and pause and I'll upload the next one. The next problem reads, for a certain bacteria, the growth constant is 0.825 when time is measured in days. Okay, stop for a second here. The growth constant, this time they give that to you, so it looks like R has been given to us when time is measured in days. How long will it take for 20 bacteria to increase to 2,000? Well, if I'm talking about the growth of a bacteria, then the smaller number is going to be my initial amount or my principal amount, and the resulting amount is going to be A. And in this case, they're saying how long will something take? That means that we are trying to solve for time. So let's go ahead and plug all this stuff in. That means that 2,000 is going to equal 20E, right, because E is always the same, R to the 0.825T. This is the same type of problem that we dealt with before, except now we're just solving for something a little bit different. So that's going to go away, that's going to go away. 200 divided by 2 is 100 equals E to the 0.825T. Let's go and take the ln of both sides. And I think you're kind of getting the hang of this by now. We know that the ln of 100 is going to equal, we know those are going to cancel each other out, so it's going to be 0.825T. I'm going to go and divide by that. Oops, not T. So let's go ahead and pump this into the calculator and see what we get. I got T is approximately equal to 5.582, and in this case, we're talking about years. All right, let's go and pause and go to the next problem. Okay, number 7. This problem here, before we even start reading this problem, I want to let you know this is a double barreled question, right? And actually, there's two parts to it. And so this is where rounding error can really kind of nail you. So just make sure you're not rounding off too much. Otherwise, you'll get some answers wrong because as the years keep going on and the rabbits keep reproducing, any type of rounding error can produce many, many more rabbits than are expected. So let's go ahead and read this problem here. It says rabbits were first brought to Australia in the late 1800s. They had no natural enemies, so their numbers increased rapidly. You know what? We don't care about this information here. Assume there were 60,000 rabbits in 1865. Okay, so this sounds to me like, and there's not a whole lot of space here, so I'm going to say it sounds to me like 60,000 rabbits is my principal amount of bunnies, right? And then 1865 is year zero, right? Or year one, rather. And that in 1867 there were 2,400,000. So 2,400,000. That seems to be my resulting amount. Now between 1865 and 1867, that sounds like time. And the reason why I choose 2 is because I'm doing this in years. 2 years. Assuming the number of rabbits grew exponentially, how many rabbits would you expect in 1870? Okay, so before we even get there, let's try and figure out the rate at which these rabbits are reproducing. So I'm going to go and figure this out first. So I'm going to say 2,400,000 is equal to 60,000 e to the r times 2. So I'm going to go ahead and knock off a couple of zeros here. 1, 2, 3, 4. 1, 2, 3, 4. So I have 240 equals 6e to the 2r. I'm going to go ahead and divide by 6. So I have 40 equals e to the 2r. I'm going to go ahead and take the natural log of both sides. So I have the natural log of 40 equals 2r, right? Because the ln and the e are going to cancel each other out. So now I'm going to be very careful about this. I'm going to divide both sides by 2, and I'm going to go ahead and leave it as is. I'm not going to go and solve this yet because any type of decimal conversion that I do right now is going to create a rounding error, and I don't want that. So the first part is done. Let me go ahead and move this stuff over. I'm going to say natural log of 40 divided by 2. I'm going to go and erase this junk here. Okay, so now what it's saying is, assuming the number of rabbits grew exponentially, how many rabbits would you expect in 1870? So I can do this one of two ways. If I choose 1865 as my initial year, then 1870 is 5 years later, which means that t needs to be 5. If I decided, in blue, to use 1867 as my base year, then to 1870, that means that would be 3. And then I would have to change my numbers of rabbits based on which year I chose. I'm going to go ahead and choose 1865 as my year. So I'll do the problem in red. So what I'm going to do is I'm trying to figure out how many rabbits would I expect in 1870. So what is my new amount? What's my total amount of rabbits now? We're doing 1870 rabbits now. So A is what I'm trying to find out. That's going to be 60,000 e to the r. Well, r was natural log of 40 over 2 times 5. So now I'm going to go ahead and pump all this stuff into my calculator here. So I'm going to take the natural log of 40, and I'm going to divide that by 2. I'm going to multiply that by 5. And now I'm going to raise e to that power by using the second answer recall key. And then I'm going to multiply that by 60,000. So 1, 2, 600, 6,000, 60,000. So my total amount of rabbits, if you've been able to keep up this far, is 6071,57310.8. But that 0.8 of a bunny, he's dead, so we're not going to count him. So I'm going to put in my zeros. It looks like 607,157 bunnies. I'm sorry, 157,310 bunnies. Sorry, I lost count there. That's a lot of bunnies. Okay, too many for my taste. So that is the video on exponential growth and decay. We'll do many, many more of these examples in class. See you next time.